we could take a few questions in the panel. I think we'll just do this standing on the stage if we rather than move our seats. So, are there any questions, ladies and gentlemen? Mike.
Right. Would you have a similar skeletal adaptation at the other end? Would the shoulders be different because they were spending more time on their feet?
I'm very glad you asked that question. So this actually shows you, this was not planned, ladies and gentlemen. This is clearly great minds think alike. So this is a scapula of an Australopithecus afarensis that was published a couple of years ago. And the authors of this paper, Green and Alemseged, noted that the orientation of that scapula is much more chimp-like in an afarensis than it is a human. So you can see the scapula in a modern human, which points a bit laterally. Chimps and gorillas are a bit more forward, a bit more cranially. And their interpretation, I think I actually have they quantified it, right? And so here's our that's the hobbit, you remember, who has a very modern-looking human scapula, at least in terms of the orientation of the glenoid fossa for the humerus. So yeah, you do see adaptations in the forelimb as well. Clearly, Lucy, at least afarensis, was not an identical kind of biped as you and I.
Thank you. Any more? Yeah.
Could I ask you if there's anything from the dinosaur period which we are perhaps part of, or was it absolutely a one-time thing, they became completely extinct?
I'm happy to say that the dinosaurs are certainly not extinct. You have seen several dinosaurs during the course of the last 24 hours. They're called pigeons or crows or parakeets. The birds nest, no pun intended, within the radiation of theropod dinosaurs. So if you want to call a stegosaur a dinosaur and a T-Rex a dinosaur, you really have to call pigeons dinosaurs too. So that's a very trivial answer to your question. I mean, yes, the age of dinosaurs as Mesozoic was essentially, I mean, compared to the sort of Cambrian and Precambrian stuff what we heard about today was much more similar to life today. You may have had, I suppose, pre-Jurassic, not so much in the way of flowering plants, for example, which actually makes a big difference. But in terms of having air to breathe, at least, you're doing okay in the Mesozoic. And it was not so different than today, relatively speaking.
The front row. Yeah.
I'm just wondering about this explosion of life around the Cambrian period. How do you account for the second increase in oxygen at that time period, after that sort of billion years of stasis?
It's unclear. So some people have suggested that there may have been a change in basically the redox state of the mantle. So we always have gas that's coming out from volcanoes, right, from the mantle. And if that has a lot of electrons, for example, then it's going to continue to consume oxygen at the planet's surface, right? And some people have suggested in sort of models for mantle evolution that you may have crossed over a point where the mantle itself became more oxidized, and therefore less electrons are coming out, and therefore more oxygen can build up in the atmosphere. Another suggestion has been that you develop more stable continental margins, which allow you to bury more organic matter. So I said that photosynthesis allows us to make oxygen, which is true. But if you then use all that oxygen to respire, then you don't leave any behind. So really the reason we have oxygen on the planet is because we've learned how to bury organic material, which is also becomes fossil fuel. So some people have suggested also that in the late Neoproterozoic, you enhance the ability to bury organic material, leaving even more oxygen behind. So there's sort of competing theories on that.
Thank you. And down here in the front row.
Thank you. I've always wondered about the fact that the universe is only 14.5 billion years old. 13.5 billion. Well, what's a billion between friends? But there's hundreds of billions of galaxies and stars.
Yeah.
And apparently, correct me if I'm wrong, but our sun is very typical of.
Very typical.
90% are like ours. Our sun is about 4.5 billion years old. Has about another 5 billion years to run.
It's middle-aged. Yep.
And yet throughout the universe we have black holes, we have lots of expired suns. Apparently black holes are actually very important to the life of galaxies.
Yes, they
as
are.
potential gravitational forces.
Mhm.
Just intuitively, you would think that the age of the universe is far longer, because these trillions of stars that have gone through birth and death are basically still with the life of a particular sun is more than say 33 or 40% of the life of the entire universe.
Sure.
Can you give me a
Sure, but the reason is the lifetime of a star depends crucially on its mass.
Yeah.
Okay, and so the sun is actually a sort of third generation star. So the very first stars formed out of material that was very slightly enriched hydrogen. Okay, so the hydrogen and some lighter elements, and it's in stars that heavier elements form. So the universe, we understand how hydrogen forms, and in the very early universe we understand how the lighter elements form. But then when that first generation of stars forms, in the cores of the stars you have nuclear fusion occurring, and you start to build up the periodic table up to iron, where the binding energy turns over. And parenthetically, to get elements heavier than iron, you can only build those in non-equilibrium situations like exploding stars. Okay. So all of you have bits of supernova in you. And as that first generation of stars enriches the material in the universe, they expire and explode. And they were quite massive stars that formed. And so they have a much shorter lifetime. Okay? Some as short as hundreds of millions of years. Okay? Then as the metallicity or the enrichment factor of this material increases, plus you have more stable galactic structures in which these things are forming, you begin to form the next generation of stars, second generation of stars, which are a little bit richer, have slightly longer lifespans. And our sun, you can look at its metallicity, is a population 3 star. It's a third generation. It's the sort of grandson or daughter of the original generation of stars that formed, and it has a slightly longer lifetime.
So we'll take that one there. Yeah.
We've just landed a little spaceship on a comet. I'm curious to know from, I guess, dropped, bounced. What the discoveries that are going to be made on that comet? What new things is that going to tell us about the origins of the universe and the origins of life?
The origins of the universe. It's more to do with the origins of life, so it's kind of at the cusp, really, of what I was discussing and what Sasha was discussing. So the question is, what elements are on that comet, and whether or not, as you saw at the end, the very last slide of my presentation, the Earth suffered a period of heavy bombardment, and it's when it was forming. And the question is whether that material, comets and the like, material on those helped enrich the mineral content of the Earth, whether it brought water with it, whether it brought more complicated molecules, perhaps hydrocarbon molecules and the like. So I think understanding the chemical constituents of comets will help us to have a much better idea of how the mineral enrichment of the Earth happened. And it's right at that cusp between where my slides finished and Sasha started. So do you want to?
I was just going to add that comet impacts on the planet have been invoked to cause mass extinctions as well. And so we see geochemical changes in rocks at certain boundaries where we see major changes in biology as well. And so another thing that potentially could be learned is whether or not we're right about that hypothesis that comet impacts can be as important as, say, meteor impacts, right, in causing disruption to evolutionary processes.
I think we can take 2 more questions and then perhaps we should finish. Yes, this gentleman here. Yeah.
Thank you. You showed the structure of the universe as like a honeycomb.
Yeah.
But we're also looking at the periphery of that honeycomb, sponge-like thing, backwards in time.
Okay.
So I'm trying to visualize something we see as a 3-dimensional architecture.
Yes.
But the outer elements of it are not today won't be as we saw them or see them.
Sure.
Now, you also said that these filaments condense. So is there evidence showing that at the periphery, the filaments are fatter?
No, so it takes a while to get your mind around how to think about cosmology, because as you look out into the universe, I mentioned briefly, because of the finite speed of light, you're looking backwards in time, right? So what I was showing you in those physical simulations of what was going on, that is the universe, the three-dimensional structure in the universe at fixed points in time. Okay. But when we look out into the universe, you're at one point in that, and as you look back, you're seeing the universe in earlier and earlier stages of its evolution. And so you have two things going on. You have that structure formation process, but then you're observing that the further you look, you're seeing that at different stages of that process. So indeed, you can see, for example, that if you look at galaxies that have low redshift, nearby, okay, you're looking at them recently, and they are far more stable entities. They tend to be largely spiral galaxies, some ellipticals. If you look at galaxies with a higher redshift, so you're looking at them further back in time, you can see them, right? It's taken longer for the light to get to you. Then there is a larger number of irregular galaxies. And that's because you're looking out, and if you remember the bit of the movie where I was showing you galaxy formation, you get you get galaxy-sized objects forming, and they'll stabilize for a while and build a disk around them. But a couple of billion years ago or more, say 4 or 5 billion years ago, longer, those galaxies are interacting more. And so you see these peculiar structures in the galaxies, more of those at the galaxies that are at higher redshift, i.e. the galaxies you're looking further back in time when you observe them. And so that process of looking out into the universe and seeing it actually happen as you look further and further away is how we build this picture together. And we can actually look back right to the point where the universe becomes opaque. I had a little slide which we called it the cosmic microwave background, and that is the oldest light in the universe. So if you imagine you're looking further and further out into space, and so you're looking further and further back in time, you can actually get to the point at which the universe in its history becomes transparent, or looking backwards becomes opaque. Because very early on in the history of the universe, it was so hot that electrons and protons weren't together in hydrogen atoms, and so light particles bounced off the electrons. As it cools, they combine, and then light particles can travel essentially unhindered. And we see that today as the cosmic microwave background, and that provides the backdrop to all our observations. And those fluctuations I showed you, those are actually real mapped fluctuations. That's what I do. That's actually my research, mapping those very early fluctuations. So we can see those, and the idea is understanding how those 1 in a million level fluctuations evolve to give us all of the cosmic structure we see. So by looking at different redshifts, you see every stage of this cosmic evolution. Does that answer your question? No, that's not the slide. But it was a valiant effort.
One more. I think we have time for one more question. But best we'll take this man here. Is that, yeah? Sorry, we can't get everyone.
Those simulations that you showed describing the galactic and cluster formation, did they take into account what we believe is the gravitational influence of dark matter?
Yes. So obviously, with 20 minutes to do 9 billion years, it wasn't possible to go into it. They take into account, those simulations are actually from friends and colleagues of mine, and they do indeed incorporate dark matter as part of the material in those simulations. What you're seeing is only the luminous parts in most of those, okay? In some of them, in the Millennium simulation, you're actually seeing all of it. But the influence of the dark matter is included in those, as is the influence of non-zero cosmological constant dark energy. It's all included in those simulations. It's only when you put those in, particularly the dark matter, that you get something that looks like the universe today. If you don't, then the statistical structure that you get out of those simulations doesn't look like what you see in the actual galaxy distribution that I showed. Remember the 2DF measurement of that large-scale sort of bathroom loofah type structure. You don't get that unless you include the dark matter component. So it's not really the key, the clincher for dark matter really is that you just wouldn't get a universe that on the larger scales look anything like our current universe without it. But obviously there wasn't time to go into that. That's another story.
Thank you. I think we must pull up the drawbridge there. And there is tea in the Grahamstorium. Would you please join me in thanking our three speakers for an absolutely fascinating afternoon? Thank you.